In this video, we're going to continue our discussion of different methods to perform numerical integration. And in particular, we're going to talk about the Simpsons rule. So there are two different Simpsons rule formulations that we will discuss. First, the Simpsons 1/3 rule, and then the Simpsons 3/8 rule. So we will go through these two methods in detail. So first, let's talk about the Simpsons 1/3 rule. So we have our function f defined on the interval from a to b. We divide the interval a to b into many subintervals, and then using the Simpsons 1/3 rule, we approximate the area under the curve in every subinterval by interpolating between the values of the function at the midpoint and the ends of the subinterval. So on each subinterval, the curve to be integrated is a parabola. So the figure shown here shows one of those intervals with the parabola going between xi minus 1, the midpoint xmi, and xi. So for simplicity, the width of each subinterval is chosen to be constant and is equal to 2h. So if n is the number of intervals, with a is equal to x0 up to xn is equal to b, and a constant spacing of 2h between xi and xi minus 1, then each interval with endpoints xi minus 1 and xi, a Lagrange polynomial can be used to define the interpolating parabola as follows. So this is, if you recall the Lagrange polynomial formulation, this shows a parabola between xi minus 1 and xi, also passing through the midpoint xmi in this case. So xmi is the midpoint of this interval I. So again, just rewriting the polynomial here, and then integrating this yields the expression shown here. So over one interval from xi minus 1 to xi, the estimate of the integral here is h over 3 times f at xi minus 1 plus 4f of xmi plus f of xi. So the integral over the entire domain can then be implemented as shown here. So it's the sum of h over 3 times, it's h over 3 times the sum as I goes from 1 to n of this expression of these values here. So it's called Simpsons 1/3 rule because we end up having this 1/3 coefficient. And this is kind of what the formula looks like if you expand it out for several points. So this figure shows the implementation of the Simpsons 1/3 rule for integrating the function defined here between 0 and 1.5. And so this is with using n equals 3. So you can see that we've got one parabola here. Between these 3 points, one parabola. This is our second parabola and our third parabola. So where these are the kind of endpoints of the parabola, and this would be the midpoint. So the exact integral for this is 6.6933, and the estimate using 3 intervals is 6.2083. So we can take a look at the error analysis here to estimate the upper bound of the error. Now we could use the same procedure that we talked about for the trapezoid rule. It turns out that there are several ways to arrive at the estimate of the error. And in this case, using Newton interpolating polynomials provides a better estimate. So that's what we will discuss here. So basically, if we can find a Newton interpolating polynomial through the points xi minus 1, xm, xi, and xi plus h. And the reason that we add an extra point, this xi plus h, is going to become apparent when the integration is carried out. So the error term between the interpolating polynomial and the function is found through the following procedures. So we can define this Newton interpolating polynomial as shown here, where in this case xi is within our interval xi minus 1 to xi plus h, and it is dependent on x. So just rewriting this, we can see that the first 3 terms on the right-hand side are exactly the interpolating parabola passing through our 3 points defined as here. So our I minus 1, our m, and our xi points. So this means an estimate of the error can be evaluated as here. So our actual function minus our parabola estimate, and then integrating that over our interval. And so we know from the expression on the previous slide that we can replace all of that with the expression shown here. And then we can perform this integration. And so this first term would actually go to 0, noting that xm is the midpoint between xi minus 1 and xi. And so this is why we added that extra point, because this term goes to 0, so this allows us to have an extra term in our equation, and you'll see that we end up with accuracy related to h to the power 5 for this interval. So the upper bound of the error for the integral is shown here. And we can perform this integration, and we get 4h to the power 5 over 15. And so just simplifying this down, combining all the constants together, we have that the error on one interval, the upper bound is related to h to the power 5 over 90. So this was for one interval, and so if n is the number of subdivisions where each subdivision has a width of 2h, so n times 2h is equal to b minus a, then the error of the integral over the total domain is just is going to be n times ei. So we can plug that into our expression for the upper bound of the error and simplify this out to say that the upper bound of the error for the entire domain is related to the fourth derivative of the function evaluated at xi, where xi is whatever maximizes this expression within our interval a to b, times b minus a h to the power 4 over 180. So for the entire domain, the Simpsons 1/3 rule is fourth order accurate, and the magnitude of the coefficient here is 1 over 180. So let's look at our same example, looking at the function f of x is equal to e to the power x on the interval from 0 to 2. We want to use the Simpsons 1/3 rule with n equals 2 to calculate our approximation of the integral and compare with the exact integral of the function. And then we want to find the value of h so that the error is less than 0.001. So it's important to note that n is the number of intervals on which a parabola is defined. So n is the number of parabolas. So each interval has a width of 2h. So that means h is equal to b minus a over 2n. So in this case, h is equal to 0.5 if n is equal to 2. So again, we have our points at all of our, with our spacing h, and our function evaluated all of those points. So according to the Simpsons 1/3 rule, we have the formulation shown here, and we can expand this out with the number of points that we're using in this problem, plug in all of our values, and we can get our estimate for the integral as 6.391, and you can see graphically what it looks like here, and you can see that this provides a very good approximation to the exact value, even though we only use 2 intervals. So basically the 2 intervals would be defined here. So we've got one parabola defined here, and then another parabola defined here. So the total error obtained when h is 0.5 is less than the error bounds obtained from our previous formulation. So for IS1, the error in the estimation is bounded by the expression here. So we can plug in our values, and we see that the upper bound of our error should be 0.0051. And we can calculate our actual error with this estimate, which is 0.002, so that is indeed less than the upper bound. And the same formula can be used to find the value of h so that the error is bounded by 0.001. So again, this is just our same formula, and we can use this to find the value of h. So in this case, h is equal to 0.33. So to guarantee an error less than 0.001 using Simpsons 1/3 rule, the interval will have to be divided into approximately 4 intervals with a parabola defined on each, which is shown here, and so in this case the estimate of our integral is 6.3892, which gives an error of 0.0001377. Okay, so let's look at the Simpsons 3/8 rule. So it's quite similar, but in this case we are going to divide, we're going to approximate the area under the curve in every subinterval by interpolating between the values of the function at the ends as well as two intermediate points. So in this case, each subinterval, the curve is going to be integrated, that to be integrated is a cubic polynomial. And for simplicity, the width of each subinterval is chosen to be constant and is equal to 3h in this case. So if n is the number of intervals, a is equal to x0 up to xn is equal to b with a constant spacing of 3h, then the intermediate points for the interval are denoted xli, which is equal to xi minus 1 plus h, and xri, which is xi minus 1 plus 2h. So on each interval with n points xi minus 1 and xi, the Lagrange polynomials can be used to define the interpolating cubic as shown here. So in the graphic here, basically we've got these, our interval defined between here and here. We've got our two intermediate points, and we define a cubic polynomial that passes between all of those points. And if we integrate that, we get the expression shown here. So this is the approximation of our integral for one interval. So then if we, to find the approximation of our integral over the entire domain, we just add up the areas of all those integrals, or all those intervals, as shown here. So the Simpsons 3/8 rule is implemented as this. So 3h over 8 times this sum of f of xi minus 1 plus 3 f of xli plus 3 times f of xri plus f of xi, as I goes from 1 to n. So it's called the 3/8 rule because we get this 3 over 8 coefficient here. And this is what it looks like if you expand it out for a few points. So this figure shows the implementation of the Simpsons 3/8 rule for our function defined here on the interval from 0 to 1.5. And using 3 subintervals, so n is equal to 3, we get an estimate of 6.5123 compared to the exact, which is 6.6933. So here we've got n is equal to 3, so this is one interval defined through those 4 points, so the 2 endpoints plus the 2 midpoints. This is the next interval with our cubic polynomial here, and this is the third interval with our cubic polynomial here through our 4 points. So to estimate the upper bound of the error, we can use the same process that we used for the trapezoid rule in this case. So given a function f and its interpolating polynomial of degree n, Pn of x, so the error term between the interpolating polynomial and the function is given by the expression shown here. So again, I'm not going to go through the proof, but if you're interested, you can take a look at the link there to kind of see how this comes about. And again, c is in the domain of the function f and is dependent on the point x. So the error in the calculation of polynomial number I, connecting the points xi minus 1, xli, which is xi minus 1 plus h, xri, which is xi minus 1 plus 2h, and xi, is estimated based on that preceding formula, assuming that 3h is equal to xi minus 1. So the error on one interval is our function minus this interpolating polynomial p3 of x. And we can replace, looking at the previous formula, we can replace this expression with what is shown here. And so the upper bound of the error for the integral on our interval I is given by this shown here. So it's the max c in the interval from xi minus 1 to xi, f, the fourth derivative of f evaluated at c over 4 factorial times this integral. And if we integrate this out and simplify, we get the expression shown here. So you can see that it is related to 3h to the power 5 over 80. So that was for one interval, and if n is the number of subdivisions where each subdivision has a width of 3h, so n times 3h is equal to b minus a, then the area of the integral over the total domain is equal to n times zi. So just multiplying our expression here by n, and using this relationship between n and h and b minus a, we can see that the area of the integral over the total domain is related to the fourth derivative evaluated at c times b minus a h to the power 4 over 80. So the entire domain, the Simpsons 3/8 rule, is also fourth order accurate. And you can see that the coefficient here is 1 over 80, which is a bit higher than it was for the Simpsons 1/3 rule. So let's again look at our example. So using the Simpsons 3/8 rule with n equals 1, we want to calculate IS2 and compare with the exact integral for the function f of x is equal to e to the power x on the interval from 0 to 2. And then find the value of h so that the error is less than 0.001. So again, it's important to note that n is the number of intervals on which a cubic polynomial is defined. So n is the number of polynomials. So each interval has a width of 3h, which means we can calculate h is equal to b minus a over 3n. So in this case, h is equal to 0.6667. So we can find our x's at all of our, with our spacing of h, and our function values at all of our points, and plug those into the formulation of the Simpsons 3/8 rule, which is shown here. So we can expand this out for all of the points that we have and plug in our values, as we can see here. So the estimate of the integral over the domain using the Simpsons 3/8 rule is equal to 6.403. So this is a very good approximation to the exact value, even though we only used one interval. So all 4 points, there's only one cubic polynomial that passes through here. So the total error obtained with h is equal to 0.6667 is indeed less than the error bounds obtained by our maximum upper bound formula, which says that the maximum upper bound should be equal to the expression here, and if we plug in our values, we see that the maximum error should be 0.0365. We calculate our actual error, we get 0.017, which is indeed less than this upper bound. So the same formula can be used to find the value of h so that the error is bounded by 0.001. So in this case, we have e to the power 2 times 2 minus 0, h to the power 4 over 80 is equal to 0.001, and we can solve for h, and we find that h is 0.27125. So to guarantee an error less than 0.001 using IS2, or the Simpsons 3/8 rule, the interval will have to be divided into 3 intervals with the cubic polynomial defined on each. And doing that, we get an estimation of our integral as 6.38925, which gives us an error of 0.000192. And you can see graphically what that looks like, and you see that we get a very good representation of the error under the curve, area under the curve.